So for 8.2, we're going to make one video here. We'll do vocab, and then we'll do the reading got it's. Factors are nothing more than numbers or expressions multiplied together to get a product. So for example, the factors of 25. Factors of 25. You guys might use factor trees might use cake, all kinds of things. Anyway, are, say, 5 and 5. Or the factors of 18x could be 18 and x. And you could say the factors of 18, you could pick 2 and 9. And then 3 and 3. And or you could say the factors 18 are 6 times 3. Any number of things. But again, factors are any numbers you multiply together to get a product. The greatest common factor is a little more specific. The words, mean pretty much what they sound like here. It is the largest of all the factors that are common between two or more expressions. So again, of all the common factors of two or more expressions, it's the biggest. So for example, if I wanted to find the GCF, or the greatest common factor of these three, we could list out, the factors, right, all the prime factorization, if you will, and then find those that are common, right? So 5, 5, 5 here, and here an x, x, and x. So 5x will be the greatest common factor of all three of these together. Now, we talked about, when you're in 7th grade, you probably use the cake method. I'll talk about that in my examples today. One of the main things you need to understand today is this idea of distributor property, which you do know. So if I have 2x times this expression, I multiply the 2x times everybody inside, so 2x times 3x plus 1. 2x times 3x is 6x squared, right? And 2x times 1 is just 2x. So this would be the distributed form of this statement. And this kind of shows the idea of how you get that. So the 2x times the 3x plus 1, and why we get all the different pieces we do, sort of a graphic representation. I'm going to use this later on when we factor, which is the reverse of distributing, so we'll talk about that later on in more detail. So here we have multiplying a monomial and a trinomial. So distributing this negative x cubed to everybody inside. Please, again, don't lose that negative out in front. So we have the negative x cubed times 9x to the 4th becomes negative 9x to the 7th. Again, using your rules, x cubed, x 4th becomes x to the 7th. This is why I told you had to learn all those rules. Over here we have negative x cubed times negative 2x to the cubed. That's going to become positive. Make sure you note that negative times negative is positive. And x cubed times x cubed is x to the 6th, and the 2 comes along for the ride. And then again, negative x cubed times 7 becomes negative 7x cubed. And that is the distributed form, again, of this expression. So what we're looking for here is distributing this 5n to everybody inside. So again, just a reminder, the 5n times this guy, and times this guy. So 5 times 3 is 15. N times n cubed is n to the 4th. 5 times negative n squared becomes negative 5 against n1 and n squared, so it becomes n cubed. And 5 times 8 is 40, and the n comes along for the ride. Okay, so one piece at a time here. And again, remembering your rules, things like n to the 1st times n to the cubed is n to the 4th, because we add them when we're multiplying the same base. Here, n1 n squared becomes n cubed. There you go. Now, we can see here we're finding the greatest common factor of this set of numbers. And we had talked about in the last one that they did it by listing out all the prime factors. So, again, the prime factorization method, and then finding the common ones. You can see the 5's in red and the x's in blue. I like to use what I call the cake method. I know you've seen it before. This was the most delicious looking cake I could find online. But anyway, let me show you what that looks like here, just as a reminder. So if I start out with my 5x cubed, and then 25x squared, and 45x. We go ahead and we factor out, I start with the numbers, right? The smallest prime that goes in all three of these numbers is the number 5. Leaving me, I should say expressions, not numbers, x cubed, 5x squared, and 9x, right? So it's upside down division. And as a reminder, I divided this 5 out of everybody. Now I'm out of common numbers among them, right? Common factors that are numbers. So it's time to look at variables, and I can see that I can take an x out of each of these. So divided on x, I get x squared, and here we get 5x, and here just a 9. And I'm done. There's no more common factors among these three at all. So my greatest common factor is over here on the left, so that is 5x. And you can see that is the answer they got as well. So again, 5x is the GCF of these three. What that means, if I were to divide this out, technically this is 5x times x squared, right, plus 5x plus 9. That's really what that means. So it's kind of getting that idea of factoring in your head of what we're going to do with this. It's going to be more complicated later, but this is a nice start. I'm going to once again use the cake method on this one. So I'm just going to write my three factors in the cake. I've got 3x to the fourth, 9x squared, and 12x. And again, we're going to start out by dividing out the common numbers among them, right, in the coefficients. And I can clearly see the smallest prime that goes in all three of these is the number 3. So that's going to leave me with x to the fourth, 3x squared, and 4x. And then, so since I'm out of coefficients here that are common among all three, I'm going to divide out the variables. And I can see that I can certainly take an x out of all these. So I've got x cubed and 3x and 4. And there's nothing left in common among the three, so my GCF on the left side here is 3x. This gets at what we talked about in the example before we did the got it. So again, you find the GCF of this statement, and whatever's left afterwards goes inside the parentheses. I'm going to show you this one in cake method just to make sure we get what I'm talking about. So again, I'm going to take that 4x to the fifth minus 24x cubed plus 8x, put the whole thing in the cake. And I always start, I know you can all see, ooh, take out a 4, right? I always just start with the smallest prime that goes in all of them. That we don't miss any numbers. And you can do it if you have another method that works better. I have no problem with that. But I know a 2 goes in all these because they're even. So this becomes 2x to the fifth minus 12x cubed plus 4x. And I can see by looking at all the coefficients, there's still another 2 in there. So I'm going to go ahead and take it out. Divide out a 2, so I'm going to get x to the fifth minus 6x cubed plus 2x. Now I can see I'm clearly out of coefficients that are common among all three. You can see the 6 and the 2 have something in common, but that doesn't help me when it comes to the x to the fifth. So now I can see I can take an x out of all of them, so I'm going to do that. So we're going to have x to the fourth minus 6x squared plus 2. And now we're out of out of variables. So I have this, right? 2 times 2 times x, which is 4x, times whatever's left here. X to the fourth minus 6x squared plus 2. And I do believe that's the exact same answer that they got. Again, I like my method, the cake method. You're welcome to use any method you like that works for you. If you just see the common factor and pull it out, I have no problem with that. So let's start with the first example here. We're going to take that 9x to the sixth plus 15x to the fourth plus 12x squared. And we're going to throw that into the cake. And we can see we can start by taking out a 3 from all three. So we get 3x to the sixth plus 5x to the fourth plus 4. Oops, I forgot the 2 there. That's why it looks so funny. That's 12x squared plus 4x squared. Now if we take a look, I can see there's no more coefficients, or no more common factors among all three coefficients. So I'm going to take a look here and go, well, what can I take out of the rest of our variables go? You notice you can definitely take an x squared out of all of them. So instead of taking one x at a time, if you'd like to, you can just take out x squared. So it's going to leave me 3x to the fourth plus 5x squared plus 4. And again, what does that mean? That means this is the greatest common factor, 3x squared, times all this is left over, 3x to the fourth plus 5x squared plus 4. So that is the factored form here as far as taking out the greatest common factor. You'll learn later maybe there's more I can do with this other part, but we'll worry about that later. We'll throw that off to the side, and we're going to do the second one. This one says, hey, what is this expression written as the product of a polynomial with positive coefficients and a monomial? So the negative is going to come out in the monomial. So we're going to have negative 6x to the fourth minus 18x cubed minus 12x squared. And we're going to recognize we can take out a negative 2. That's what's going to allow everything inside the parentheses to become positive. So this becomes positive 3x to the fourth plus 9, so positive, right, x cubed, plus 6x squared. And we notice there's still a 3 we can factor out, so I'm going to do that. 3, and then we get x to the fourth plus 3x cubed plus 2x squared. And hopefully you recognize we can take out an x squared among all this. So all of them in there, if you look at the variables, have an x squared in common. So I'm going to do that in just one shot. So x squared plus 3x plus 2. So again, what does that mean? That means the stuff on the side multiplied, negative 2 times 3 times x squared. So that becomes negative 6x squared. And then in parentheses, this stuff. So I'm going to get x squared plus 3x plus 2. And again, later on we'll learn maybe there's something more we can do with the parentheses. The parentheses here. And maybe there is. Maybe I can factor that more. But we're not worried about that part today. But I bet you maybe. Before we actually do this problem, I want to make sure we understand that factoring is nothing more than dividing. So when I go back to those other examples I did, we were doing nothing more than dividing out a term. Okay, so that having been said, this is kind of a fun story problem. A helicopter landing pad, or helipad, is sometimes marked with a circle inside a square so it is visible from the air. What is the area of the shaded region of the helipad at the right? Write your answer in factored form. So what I'm saying is I take this square, right, and I subtract the circle from it. So in order to do that, we need to consider the formulas for area of a circle, area of a square. So if I look up here, area of a square, we're calling that A1 is s squared, right? Or in this case, since a side is 2x, it's 2x, the whole thing squared, which is 4x squared. Okay, let me repeat that to you. So the area of the square is a side squared, right? We know that. And we said a side is 2x, so it's really 2x squared. So you can see that here. And when we do that, we get 4x squared for the area of the square. That's if there wasn't a circle punched out of it. Area of a circle is pi r squared. Well, we can see that radius is x here. So we plug that for radius, plug in the x, so the area for this circle is pi x squared. So the overall area, if we take this square minus the circle, is a1 minus a2, or 4x squared minus pi x squared. And then what the factored form of this. So this is technically the area, right? It's a formula for the area of this one, whatever x happens to be. So the factoring form of that, again, you can use cake method, whatever you want. We find the GCF is certainly x squared. So we factor that out, and we get x squared times 4 minus pi, which remember, pi is a number. So that is going to help us find the area of just the red shaded region up here. This time around we have to make the assumption that the side length is instead 6x. So we're going to draw a pretty picture here. Whoops. There we go. Draw a pretty picture of my square minus a circle. And again, we're looking for that shaded region around the outside, right? We want that area. And we said this time the side is 6x. That means the radius across is 3x. So I'm going to work mine slightly different than they did. I'm going to say I'm going to have the area of a square minus the area of a circle. Area of a square is side squared. Area of a circle is pi r squared. Now, I know a side is 6x, so I'm going to plug that in. I'm going to have 6x squared minus pi, and the radius is 3, right? So 3x squared. This part was nothing more than substitution. So again, look over here with me. There's the radius, there's a side. I just substitute those in for the formula. Now it's time to do the math work. 6x squared, well that's 6 squared and x squared, so that's 36x 36. Better erase that, I guess. That is 36 x squared. And again, this is why I said learn all those rules, right? So you know where I got that. Minus pi times 9x squared. I'm going to rewrite this so it looks a little more standard. 3x squared minus 9 pi x squared. Because pi is a number, it is not a variable. Okay, so I need to find the greatest common factor among these. I'm going to stick that in the cake. I lost that 6 again. There we go. So 36 x squared minus 9 pi x squared. And, you know, we can see that there's clearly a 9 in the 36 and a 9 in the 9, right? So instead of going 3 by 3, if you want to just divide out, take out a 9, leaving us with 4x squared minus pi x squared. Now, there's no more common factors. 4 and pi have no common factors. But I can clearly see there's an x squared in both. So divide that out. So I'm going to get 4 minus pi. So when it comes down to it, I've got this 9x squared times this 4 minus pi. And you could estimate that if you wanted to, but there's no need to because I want an exact answer. So this is my factored form of the statement related to the area of the red, right, my pretty picture up here, of the red part of the helipad.